Think about the mechanics of a robotic arm assembling a complex structure. The execution takes time. It is a continuous process. Standard synchronous tools in ROS expect quick, immediate responses. When a task requires minutes or hours to complete, those basic tools block the system and halt operations. To handle long-running operations, developers use ROS actions. Actions operate as an asynchronous communication mechanism. They allow a node to send a goal, receive live status updates as the task progresses, and collect a final result without pausing the rest of the system. In this guide, we are building a complete Python pipeline to manage these tasks. We will write a custom action server to execute operations, an action client to request them, and we will process the live feedback loop between the two. Before we write the code, check these 3 prerequisites. You need an active ROS installation on your system, a basic understanding of Python programming, and a configured ROS workspace ready to accept new packages. If you forced a simple synchronous service to handle a heavy task, your robot's main process would freeze while waiting for completion. Using an action keeps the node responsive, allowing the system to monitor sensors or process other commands while the primary task runs in the background. Step 1 is defining our data structure. Open your ROS package, create a new directory named action, and inside it, initialize a blank file called youraction.action. This file has 3 parts. First is the goal definition, telling the server what to achieve, declaring an integer target position. Next, the result establishes the outcome, assigning a Boolean for success. Finally, the feedback defines a live data stream tracking the current position. Save the .action file, open your terminal, navigate to your workspace root, and run catcan-make. This translates your raw text file into usable Python message classes that our scripts will import. Watch the terminal output closely. If the action generation logs do not appear during the build, you have a configuration issue. Pause here and verify that your cmakelists.txt and package.xml files declare the correct dependencies. This compiled file acts as a strict structural contract, guaranteeing the client and server format their data using the exact same language. Next, create a new Python script for the server. We will build this node using the simple action server class provided by the ActionLib library. Look at the top of the script. We bring in 3 specific imports mapping to our generated messages. Inside initialization, we bind simple action server to the youraction namespace. Finally, rospy.spin tells the node to loop indefinitely, listening for incoming client requests. Even though this node loops continuously to maintain an open ear, its asynchronous design ensures it will not block your other ROS processes from running. The server is now an independent processing engine. It crunches complex operational math for extended periods, while the rest of the robot remains highly responsive. Now, create a separate Python script for the client. This side of the pipeline uses the simple action class to trigger the server we just built. We handle the incoming live data stream with a dedicated function. The feedback callback intercepts messages from the server and parses the current position. In the main block, we initialize the client. Firmly, before sending a goal, you must call client.waitForServer. Skipping this specific command causes silent failures. If you fire a goal into a disconnected void, the robot will stall indefinitely, waiting for a response. To test the architecture, open multiple terminal windows. Boot up ROS core in the first, launch the server in the second, and run the client node third. Look at the client terminal. You should see a continuous stream of position updates rapidly scrolling as the server executes the goal. The top pane processes the primary task, while the bottom pane seamlessly logs incoming data, proving the system is running asynchronously. When you verify this live data stream, you have confirmation that the communication loop is closed and the underlying architecture is fully functional. You have successfully engineered a fully asynchronous ROS action pipeline from scratch. While our tutorial used simple placeholder numbers, this asynchronous architecture provides the standard framework for managing hardware-intensive tasks. In production environments, these seam server-client loops coordinate complex robotic manipulation, navigation, and persistent data collection. If you run into issues as you scale, check the server's publication loop frequency to diagnose feedback delays. If you face connection failures, pull up your ROS network logs to ensure your nodes are communicating over the correct ports. Mastering these asynchronous loops allow you to build ROS applications that remain responsive during long-running operations. You can now design systems that monitor their own progress and react to changing goals in real time.